Hello, this is the course of data structure and algorithms. So in this section, I would like to explain about the concept of tree. So we already learned about single linked list, double linked list, and stack, queue. So we move forward to another concept. We call it tree. So there are three things that we will learn here about the tree and the traversal in tree and the other kind of tree. Yeah. Tree ADT. ADT, as you know, this is the abstract data type. Okay? So yeah, this is one example about a tree. But what is tree in the computer science? You know the tree in the natural. Okay, the tree is the namu. Okay, but in computer science, a tree is an abstract model of a hierarchical structure. So we have the hierarchy. Okay, so this is the key idea. For example, we have a company. Okay, the company is name is Computer RS. Okay, and then they have the sales department, they have the manufacturing department, they have the R&D department, and then let's suppose the sales department has the US region and international region, and for the international region we have the Europe, we have Asia and Canada. Okay, and then manufacturing, they are division for laptops and they are division for desktop, as for example. So a tree consists of nodes. So we call this is one node and this is another node. Okay, and we have the parent child relation. So this is the parent, okay, and this is child. If we are looking at this node, then this is the parent and this is the child. If we are looking at this one, then we call this is the parent and this is the child. Oh, sorry, this one is the parent. This is the parent and this is the child. So we have the parent and child relation for every of this node. The application could be in the organization charts, okay, and it can be a file system or it can be in a programming environment. Some terminology on the tree is like this one. First, you need to understand the root. Okay, what is the root? Root is node without parent. So A, this is, there is no parent. Okay, there is no upper node. So it means we call it, this is the root. And there is another concept you need to understand, which is the internal node and external node. So the internal node is node with at least one child. So we, for example, it is A, B, C, and F. Okay. So A has 3 children. Okay, so it means A is internal node because at least one child. B is also an internal node because it has two children. F is also internal node because it has 3 children. C is internal node because it has 2 children. Okay. What about the external node? External node means we have no children. Okay, node without children, or sometimes we call it as leaf. For example, E. Okay, E, there is no children. I, J, K, G, H, and D. There is no children. Okay. And then we need to understand the ancestors. So the ancestors means the upper of the node. For example, parent or grandparent or grandparent. Let's see, I have I. What is the parent of I? Yeah, the parent of I is F. Okay, I have the node J. What is the grandparent? Okay, what is the grandparent of J? Then yes, B is the grandparent of J. Okay. And what about A? A is the grandparent. Okay. So you can see the structure. If it is going up and up and up, yeah, we can see as the ancestors. And what about the node depth? We have the concept of depth. It is to indicate how many of the ancestors. Okay, so if we have this one, two, and three, so the depth of the node means the number of ancestors. If we are making, if you are going to understand the J and then going to P, okay, so the depth means two. Okay, or if we are in the E and then I want to know the parent, okay, the depth is one. So it means the number of ancestors either upward or downward. And then you can define also the height of the tree. The height of the tree is the maximum depth of any node. We know that A to C is 1, A to G is 2, but there is another maximum which is A to I, it is 3. So I can say that the height of the tree, which is the maximum, is 3. Yeah. We can also have another concept like descendant. Descendant means the child, grandchild, grandchild. So the same with the ancestors. Okay. So if you are moving downward, then you have the child, grandchild, grandchild. If you're moving upward, then you have parent, grandparent, and grandparent. So we call subtree. Okay, what is subtree? So subtree is tree consisting of node and its descendant. If we have this tree, then we can have a subtree. This is the subtree. Okay. So there can be another subtree. For example, yeah, this can be subtree and so on. Okay. So in the tree ADT, we can use the position to abstract the nodes, and then yeah, you can also use some methods. For example, the generic methods, you always see the length. It means how many elements in that ADD, and then is empty. So you want to know whether it is empty or not. And because you already learned from the previous section about the positional list, so we understand about the positions, and then we understand about the iter means the iteration. So we want to know for every element in that, for example, list. Okay, and we have accessor methods. So we want to access the element, we want to access the root. So what is the root? Okay, you know that the root is the element without parent. Okay. And we want to access the parent. And then P means the parent of node in the position P. And we want to know the children. So if the children is more than one, then we will do the iteration, or we will use the iterator. So the children of P is the position. Okay. And then we want to know, for example, the number of children of a position P. Then we can just use any class like this one, integer. And we can use the query methods. For example, I want to know whether it is a leaf or not. If it is a leaf, yeah, P is a leaf or not, the position P. If it is a leaf means we cannot find any children. Yeah, leaf is not without children. And we want to know if it is root or not. So if it is a root, then there is no parent. And then for the updating method, we can just use replace. So replace the position P with object O. Okay. Yep, you can define your own method. Okay, so you can have the methods to define the tree ADT, but for this, I think it's enough to explain about the tree ADT. So in the previous section, you learn about the position. Okay? So the class tree will reuse the position class, and you will see the element equal or not equal. Okay, and then you will have the next of the concept of tree, which is root, parent, okay? And then number of children, and then the length. And then you want to know whether it is a root or not, or it is a leaf or not, or it is empty or not. Okay. So this is the abstract tree class in Python, and whenever you use this tree, then you can have the way to access the tree. So this concept shows that whenever we have the element, or whenever we have the node, okay, so in the position we apply the node. So whenever we want to check every node, we need to understand the sequence, how we access every node. There is one concept about pre-order traversal. Okay. So the pre-order traversal means it is a traversal, so it is a traveling. Okay, so just think that we are going to travel. How to travel? Yeah, we are going to travel for every node, and we will visit the nodes of a tree in a systematic manner. So if you have a list, okay, you have a list like this one, and then you know that the element will have like the index 0, index 1, index 2, index 3, and so on. Okay. And if you want to know, for example, with the position list, yeah, you will have like the position, like before we have the 8 and the position P, and then we have like, for example, P5 in the position Q, and so on. Okay. But in this case, we are using node. Okay. So the node, where is the node? Yeah, we need to define the P, and then we need to define the child, we need to define the parent, and so on. So how to define that one? Yeah, of course, you can use the tree class ADT, which we learned before. And whenever we want to access them, we need to understand the pre-order traversal. So this pre-order traversal means I want to visit nodes before its descendants. Do you know what is descendant? Okay, descendants means the next node. Let's say this is 1. Okay, so I will visit 1 before 2. Okay, and then I will visit 2 before 3, and then I will visit 2 before 4. Okay, and then I will visit those before 5, and then I will visit those before 6. I will visit before 7, and then I will visit 8, and then finally I will visit 9. So this is the structure. So I will visit according to this sequence, and you can make the algorithm. We call it, this is pre-order algorithm. And then we want to note that every node which is V, okay, we will check it. So for example, I will like to use V, and then let's see if I visit V or not. And then whenever I visit the V, I will check for each child W of V. Okay, so it means I would like to check every child from V. So let's say if we have the V equals to 1. Okay. If V equals to 1, okay, now I will have like a kind of table like this one. So the node 1 now is visited. Okay. And for every child W of V, so we have 2, 5, and 9. So we are not visiting yet, number 2. So we will go to the child. So we will go to the child number 2, and then, oh, we have pre-order W. What is pre-order W? Oh, sorry, I guess I need to put this big O. Okay. So pre-order W means I need to do recursion. Do you still remember? So this is the recursion. So we will again check. Now we are in the node 2. Okay, so now V is after 1. Okay, I cannot change this one. Now let's say this is 2. So now we are doing the node when V equals to 2. When V equals to 2, so again we will visit 2. So visit 2. And then for each child W of V, so we know that we are now at 2. We will check what is the child of 2 Okay, we have 3. So the 3 is cited here, and then we will do the pre-order W. So the V, now we will go to 3. And then again, it will be a recursion. We will do the pre-order V. V is the 3. And then we will visit 3. So we will visit 3. And then for each child W of V, is there any child of 3? No. Okay, because there is no child. So we will finish this one. And then you know that this is a recursion. So when it is recursion, we will go back to the previous one and then check what is there any child for these two? Yes, because we already finished with 3, so we will go to 4. We will go to 4. So we will do the pre-order 4, and then again we will do the recursion. In the recursion, we will visit again. Okay, we visit the number 4, and after we finish it number 4, and then check whether there is a child of 4, because there is no child, and then we will return back to 2. Okay, and then because there is no other child in 2, so we will return back to 1. After we return back to 1, so we will go to the next looping. So we will go to the next iteration. So the next iteration will be on the next children, which is 5, and so on. We will go to for next, is 6, and then 7, and then 8, and then we return back. Is there any child? No. And then we will return back to the top of the root, and then after we are in the root, we will go to the next 9, and then after we have this one, finish. Okay, so that's the step with the pre-order. We have another traversal which called as post-order traversal. So in the post-order traversal, the node is visited after its descendant. So this is the opposite. Okay? And in order to make the algorithm, we use the post-order V. The idea is the same, but we will start from the leaf. Okay. So we have the V. Okay. So it's the same with the previous one. Let's say we have the node 1. Okay. So for every child W of V, okay, we will do post order. Okay, well, we will start with 9. Okay, so it means for every child of 9, okay, we will go post order. So we will go to 3. This is the first. Okay, and then we will go to post order. And then is there any child of 3? Yes, we have 1. Okay, so we after 3 we go to 1. So with the post order, we again go to this function, and then what is the next after 3? We have 1. Okay, after we are in the 1, is there any child of the V? Yeah, because there is no child of the V, so we just put visit V. So we will check V as 1 as visited, and then because we finish with this one, we will return back to the parent, and then we will go to the next node. Okay, we will go to the next child. What is the next child of this one? The next child is 2. So the 2 here will be cited here. Okay, so is there any child of the V? There is no child from 2. Then we will do visit. So we will visit V. So 2 is noted with V, and then after that one we will return back to 3. And then because there is no other child, okay, there is no iteration for other child, and then we will return back to the we will visit this one. Okay, we will visit V, and after we visit this one, we go to the next child. So the next child, we still have another child, so we start with this one. So 4 will be noted as V, as visit, and then we will check another, which is 5. Okay, and then we will check V, and so on. After 6, it will go to the parent, which is 7. And then again, we will check whether there is another children. Yes, we have 8 for another child. And then after we noted 8, finally, we will note the root as 9. Okay. So this kind of mechanism we can just use for the computer. So for example, when you are going to add more files, so it will check whether in your directory or in your subdirectories there is still space or not. Okay. So in the concept of trees, we can also understand about the binary trees. The idea is whenever we have the tree, we want to have only 2 children. Okay, because the word binary means only 2. If you know, binary is 0 and 1. So the same with the idea. The binary tree means a tree with the internal node has at most 2 children. Okay, so A has 2 children. So it is exactly 2. Okay. And if it is exactly 2 for every node, okay, so this is exactly 2, and then this is exactly 2, and then this is exactly 2, and this is exactly 2. Then we call it, this is the proper binary trees. Okay. The children of a node are an order pair. So these children, okay, this is what we call it order pair. So after B, we are going to C. So there is an order. Okay. After D, we have E. And after F, we have G. And after H, we have I. We call the children of an internal node left child and right child. So the internal node, do you know what is internal node? The internal node is the node that has children. So this A is an internal node. We have B and C. So we call this is the left. Okay. So we have left, and this we have right. Okay. And for this one, we have the alternative recursive. You know, the recursion is applicable to this kind of tree. Okay. So this recursive definition in the binary tree, it can be a tree consisting of a single node or a tree whose root has an ordered pair of children and each of which is a binary tree. Yeah, this is a kind of the concept when you apply this in the tree. So for example, this is the base. Okay. So when the tree is containing only a single node, then yeah, you can finish. And then it will be always a kind of recursion when they have the recursive call. Okay. Yeah, the idea is something like this one, but of course it depends on the application. So this is the alternative. Some application is for the arithmetic expression, and you can also use for the decision process or for searching. So for searching, you know already about the binary search. So the binary search is from this idea. Now you can see one example about the how to apply the tree. We can use the arithmetic expression tree. So this arithmetic expression tree, you learn from the stack. Okay? We can distinguish the tree into two. Yeah, we can have the operators as the node, and we can have the operands. So what is operators? Okay. So the internal nodes is the operator and the external nodes are the operands. So internal node means the nodes that has children. So we call this is the operators like plus or multiply or division or minus. Okay. And the operands means the number. Okay. The numbers that you want to do the operation. For example, if we have 2 multiply a minus 1 plus 3 multiplied by b, then you can make a kind of uh, this tree. Okay, so 2 multiply by a minus 1, okay, and then we are going to plus with 3 multiplied by b. Okay, so the concept of the traversal can be also represented by a tree like this one. You can also have the concept of decision tree. So if you are studying about the data mining, there is a concept about the decision tree, and this is a kind of decision that you want to do. For example, binary tree, we have the internal nodes and external nodes. The internal node is questions with yes or no, and then the external will be the decision. Let's say I want to decide where do you want to have your meal. Okay, I want to have fast meal. Then you may have question whether do you want coffee or not. Yes, maybe you can just go to Starbucks. Okay, sorry to mention brand. If you don't want to have coffee, maybe you can go to Spike. So this is a kind of bakery. Okay, if you don't want to have fast meal, so expense account. So it means you want to find not so expensive. Okay, if it is not expensive, maybe yeah, some of the restaurant is there's one restaurant called Al Forno. Yeah, that's not that uh, expensive, but if do not on expense account, then you can just go to Cafe Paragon, for example. Okay, so those kind of decision tree can be represented like this one for your decision of your daily living. Okay, I will continue with this concept on the next class. Okay, so yeah, I will stop this video recorded course and I will continue this one on the next our meeting. Thank you very much for listening. This is the class of data structure and algorithm.